In this video, we're going to discuss plotting the probability of an event using logistic regression and the data from a logistic regression. We're going to make our plot a little bit broader than what is built into SPSS. So we're going to run our stats in SPSS and then copy the results into Excel. And we're going to use the chow data on ortho-K lenses, comparing a spherical fixed parameter type lens to a, in this original data they used the custom spheric lenses. However, we are noted in that in the fixed parameter there were actually subjects that did well with the spheric lenses and subjects that did poorly, poor control. And we want to know what is the difference between a good control and a poor control. And so we don't want the spheric, so we're going to go in, we're going to select our cases, and we're going to pick the fixed parameter only. And we are going to, we have multiple eyes for each person. So we need to, since the eyes are not independent, we're going to run the analysis twice, basically replicate the study for each eye. And finally, our outcome measure, we can see spherical good control is a 0 and poor control is a 1. So that's going to be our binary outcome variable for our logistic regression. If we come down here, binary logistic, lens type 2, 0, 1, 1 being poor. So 1 is poor control. We're going to look at pupil size. Come up here, we see that our classification table, oops, we don't want that, variables in the equation. Pupil size has a positive coefficient there with an 8.43, significant. That means that since 1 was poor control, the positive number means a bigger pupil size tends to predict poor control. So it tends to be more poor control. So let's copy this, the variables in the equation, and then we have put it into Excel. This is what we just copied, this little section right here. And there's the information, one for the left eye, one for the right. Now, we'd like to, just for the heck of it, check our means. And so I did a t-test, good control, 5.3, a smaller millimeter size pupil than poor control, 6.05. Very significant. Levine's test, not significant, so we can use the top row here. Highly significant difference. All right, now what we want to do is, and I copied that in here just for the heck of it, with the group statistics and that independent test. Now what we want to do is our goal is to create this graph. And we have over here all the possible pupil sizes. Now, when we're looking at pupil size frequency, what we often do, most generally do in fact, is we go into Analyze, Descriptive, Crosstabs. We put in pupil size here, lens type there, and we say OK, and we get this crosstab. Now, this is an ugly crosstab to copy in and work with because we want to go for proportions. And these are labeled as percents. We could use it, then divide by 100. There's also 2 columns here. I'll show you a little trick that you can do. You can go into a one-way, Analyze, Compare Means, one-way, and put in lens type. And lens type, remember, is a 0 or 1 variables. So we're calculating the mean for 0 and 1 for each level of pupil size. This makes completely no sense if you're thinking in terms of statistics, because normally you would, like in the independent t-test, pupil size was up here and lens type was down here as the factor. We're going to reverse the two, because the mean based on frequencies, if you had 10 people and 7 of them had poor control, the average would be 7 ones, 3 zeros for an average of 0.7. So doing this will give us the proportion of people having a particular poor controls. It would give us the proportion of poor controls at each level of pupil. And that gives us an output that looks like this. So here was our pupil size, our I, we have our mean, standard deviation. All this came from, this is the output from the one-way ANOVA, at least describing the means. And what we like about this is that the pupil sizes are listed in a nice, neat way. The proportions, the means of zeros and ones, come out in a nice format so that we can actually graph these by just marking these two columns and inserting a scatter type graph, and we get these nice points that come along here. This is pupil size on the x-axis and proportion that were poor controls on the y. Now, what we want to do is be able to plot this line. In order to plot this line, we have to compute the predicted value for each of the pupil sizes. And so how do we do that? Well, it's just exactly like a regression equation. So we come up here and we look at our constant, D4, that's that 12. We hit the function F4 key to put in dollar signs to fix it, plus the pupil size, D3, F4 to fix the, make that a constant so it doesn't go anywhere, and multiply it times the pupil size, which is 3.5. And that gives us our logit value. We haven't gotten to the probability yet. Our logit value of minus 5.036. And then we copy this down, and we get the logits for all of them. Well, logit isn't going to do us much good. We need the probability. So the probability of the estimated probability of pupil size 3.5 is 1 divided by quantity 1 plus exponentiating it, taking it from a logit, doing the reverse of a log, and up to the model. This was our result, the logit, the model answer from the whole thing. We could have just as easily put this the model equation inside that value, but I separated them for ease. Now, one thing that's a little weird is that even though the logistic regression figured out what to do, unfortunately, they made the probability of having a really small pupil size a really high probability. So in fact, what it's doing is it's reversed, the SPSS program reversed the 0 and 1. And so it's giving us the probability of good. Well, in order to get the probability of poor fit, we just subtract 1. We subtract this value from 1. And so it's 1 minus that. So we're getting that value there. And remember, this value Well, actually, I guess I better do it the other way. This value divided by 1 minus, which is, in fact, this value, equals that number, and then the log of that gives you that number, which is darn close to that number. So, except that it's a positive. Well, maybe if I had done it the other way around, I would have come out better. But in any event, that's where we are. That's how this all works. And so we calculate this, the logit and the probability of poor. We come down here, we do it for both eyes, and then our line is that. So now you can see we have the model and a nice description of how well the data fit that model. So this gives us some idea of what our data looks like, and you can see, and how do we get these lines? Now that's a good question. Well, this line is the 50th percentile. So the model predicts that all values beyond this point are predicted to be in the poor myopia group, and all values to the left of it are in the lower 50% prediction for the good control group. So how do we get that number? Well, if we go in and solve for this regression equation, remember that the logit is the log of p over the quantity 1 minus p. When p is 0.5, that's the log of 0.5 over 1 minus 0.5, which equals 1. The log of 1 is 0. So the logit side of the equation drops out, and we're left with 0, an equation that's 0 equals a plus bx, and that's 12 is the a, the slope b is the 2.1, and so to solve this, it's minus a over b. It's a very simple equation, and that gives us the cutoff at 5.86 millimeters for the left eye and 5.83 millimeters for the right eye. You can see that's in there. And to plot that, I added this little trick up here. So that way I didn't have to figure out where I could have drawn in a line and then just moved it to where I thought was 5.86, but this gets it's exactly right. And so that's how you plot probabilities in a logistic regression problem. So you get a nice line, you get a distribution. If this model didn't fit, the dots would be all over the place, the line would be some crazy thing. So that's what we get.